The humid darkness of Surigao Strait was absolute. 20 minutes past 3 in the morning on October 25, 1944, and Rear Admiral Shoji Nishimura stood on the bridge of the battleship Yamashiro, peering into blackness so complete it seemed solid. Around him, his staff officers maintained the disciplined silence of men who had served together through 3 years of war. Behind them stretched what remained of the Imperial Japanese Navy's southern force. The heavy cruiser Mogami, her searchlights shuttered, her guns trained forward. The destroyer Shigure, already damaged from earlier torpedo attacks but still gamely maintaining formation. This was supposed to be Japan's counteroffensive, the plan that would reverse the tide. Vice Admiral Takeo Kurita's powerful center force would break through San Bernardino Strait from the north, while Nishimura's southern force thrust up through Surigao from the south. Together, they would crush the American invasion fleet at Leyte Gulf between them like a hammer and anvil. Simple, decisive, the kind of bold stroke that had won Japan its empire, except nothing had gone as planned. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Kurita had been delayed by American air attacks in the Sibian Sea. The battleship Fuso and 3 destroyers had been blown apart by American torpedo attacks just 20 minutes ago. Nishimura had received no word from Admiral Kiyohideshima's second striking force, somewhere behind him in the darkness. And now Yamashiro's radar, a Type 22 set installed just 6 months earlier with great pride, showed absolutely nothing ahead except the dark landmasses of Leyte and Dinagat Islands bracketing the strait. The Americans had to be there. Intelligence confirmed 6 battleships, 8 cruisers, dozens of destroyers. But the Type 22, with its 10-centimeter wavelength and modest 2-kilowatt power output, detected nothing but empty ocean at ranges beyond 20 kilometers. The darkness was playing tricks. Rain squalls obscured even the stars. This was as it should be, Nishimura thought. Night combat was Japan's specialty. The Imperial Navy had perfected it in brutal battles off Guadalcanal, at Columbangara, at Empress Augusta Bay. Japanese optics were superior. Japanese crews were trained for exactly these conditions. The long-lance torpedoes, carried by his ships, could strike targets 20 kilometers away. If he could just get close enough to see the Americans, close enough for visual fire control to work its precision magic, victory was still possible. At 3:25, Yamashiro's lookouts reported flashes on the horizon ahead, distant, indistinct, possibly lightning from the squalls everyone could see gathering to the northeast. Nishimura ordered all hands to battle stations. The main battery, twin triple turrets mounting 14-inch guns fore and aft, trained toward the flashes. Rangefinders extended from their armored housings. Fire control teams made final adjustments to their mechanical calculators. Everything was ready for the decisive close-range engagement Nishimura expected. Then, at 3:51, the darkness erupted into hell. The first American shells began falling around Yamashiro from a direction and distance that seemed physically impossible. 16-inch armor-piercing projectiles, each weighing over a ton, plunged from the sky at steep angles. They made a sound as they fell, a freight train roar that grew louder until the ocean around the battleship exploded in towers of white water taller than the ship's masts. Orange flashes lit the horizon, perhaps 12 miles away, maybe more, too far for accurate gunnery by any fire control system Nishimura understood. But the Americans weren't just firing randomly into darkness. The second salvo, arriving 30 seconds later, straddled Yamashiro. One shell struck aft, penetrating the deck and exploding deep in the ship's vitals. Another hit near the waterline amidships. A third demolished the portside, secondary battery, killing its entire crew instantly. Fires bloomed across the battleship's length. Damage control parties scrambled through smoke-filled passages toward flooding compartments. On Yamashiro's bridge, controlled panic spread among officers who had witnessed 3 years of war, but never anything like this. The Americans were hitting them, in total darkness, from a range so extreme that Japanese doctrine considered it beyond effective fire control, and they were hitting with their first salvos. Captain Shinoda Matsuo, Yamashiro's commanding officer, stood at his post, trying to process information that violated everything he knew about naval warfare. "Sir," he reported to Admiral Nishimura, his voice carefully controlled. "They're hitting us from extreme range. Our optical rangefinders show nothing. The Type 22 detects no surface targets, but they're hitting us." Nishimura gripped the bridge railing, feeling his flagship shudder as another salvo struck home. "Return fire," he ordered. "All batteries, bearing toward those muzzle flashes." Yamashiro's main battery roared, sending 6 14-inch shells toward where the Americans had to be. The fire control team used visual estimation of the muzzle flashes because their radar showed nothing useful at this range, and their optical rangefinders couldn't penetrate the darkness to find actual targets. It was educated guessing elevated to doctrine, the kind of thing that worked when you could see your enemy, or when you were close enough that minor errors didn't matter. But as Yamashiro's shells splashed harmlessly into empty ocean thousands of yards short of their targets, more American salvos arrived with mechanical precision. 14-inch shells from the battleships Tennessee and California joined the 16-inch fire from West Virginia. The cruisers on both flanks added their 8-inch batteries. The volume of fire was staggering. More shells were falling in a single minute than Nishimura had expected in an entire engagement. And still, every American salvo found them. Corrections came so quickly it was as if the Americans could see in the dark, could measure every change in Yamashiro's course and speed instantly, could calculate firing solutions faster than the ship could maneuver. At 4:01, a 16-inch shell penetrated Yamashiro's forward magazine. The explosion that followed lifted the 32,000-ton battleship's bow clear of the water. When she settled, the entire forward section was a ruin of twisted steel and flaming debris. The forward main battery turret, all 3 guns and their crews, simply ceased to exist. Secondary explosions rippled through the dying ship as ammunition cooked off and fuel tanks ruptured. Nishimura, thrown to the deck by the blast, pulled himself upright using the chart table. His staff officers, those still alive, stared at him with expressions he had never seen before on the faces of Imperial Navy men. Not fear exactly. Something worse, the recognition of a reality they couldn't explain and couldn't fight. "Sir," said Lieutenant Commander Yamaguchi, the ship's gunnery officer, his voice raw with smoke inhalation, "they're hitting us with every salvo. From ranges our doctrine says are impossible for accurate fire. In total darkness, I don't understand how they're doing it." Neither did Nishimura, but as he looked at the tactical plot, at the positions of the American ships marked based on their muzzle flashes, a terrible suspicion began to form. The Americans had some way to see in the dark, some way to measure range and bearing with precision that exceeded anything optical instruments could achieve, some technology that let them shoot accurately at ranges where visual fire control was useless. The word radar existed in Japanese naval terminology. The Type 22 sets on his ships were radar, but they were search radars, meant to detect aircraft or find ships at moderate ranges. The idea that radar could be used for precise fire control, that it could measure distance and bearing accurately enough to guide main battery fire at extreme ranges in total darkness, had seemed theoretically possible but practically impossible given the state of Japanese technology. Now, as Yamashiro rolled onto her side, fires consuming her from stem to stern, Nishimura understood that the Americans had solved what Japanese engineers thought was unsolvable. They had turned radar from a search tool into a fire control system. They could see in the dark. They could shoot accurately at ranges that made Japanese optical systems useless. They had transformed naval warfare into something the Imperial Navy, for all its training and courage and tactical excellence, couldn't match. At 4:08, Yamashiro capsized completely. Nishimura and most of his staff were still on the bridge when she went under. The few survivors, including Captain Shinoda, who was blown clear by an explosion, would spend hours in oil-covered water before being rescued by American ships at dawn. Out of 1,900 men aboard Yamashiro, only 10 survived to tell the story of how their battleship had been destroyed by an enemy they never saw. But Nishimura wasn't alone in his fatal confusion about American radar capabilities. The shock of Surigao Strait had been preceded by years of Japanese naval intelligence struggling to understand exactly what the Americans had achieved with radar technology. The story of that struggle, and of Japanese efforts to match or counter American advances, reveals a tragedy playing out on multiple levels: technical, industrial, philosophical, a tragedy of assumptions that proved catastrophic and knowledge that came too late to matter. To understand how Japan arrived at Surigao Strait unprepared for the American fire control advantage, you have to go back 2 years earlier to the humid morning of August 7, 1942, when U.S. Marines stormed ashore at Guadalcanal. The island, a steaming jungle-covered strip of land in the Solomon Islands chain, had seemed like a minor prize when Japanese forces seized it earlier that year. They'd begun constructing an airfield there, another link in the defensive perimeter protecting the empire's southern conquests. But American planners understood that an operational airfield at Guadalcanal would threaten Allied supply lines to Australia, so they struck first, in what would become the opening move of America's Pacific counteroffensive. The Marines took the airfield quickly. The Japanese, caught by surprise, withdrew into the jungle. In the chaos of evacuation, they left behind vast quantities of equipment, documents, and partially destroyed facilities. Among the material abandoned was something that would fundamentally change Japanese understanding of American technology: an intact radar installation. Lieutenant Commander Yasuda Masao of the Imperial Navy's Technical Research Division arrived at Guadalcanal on September 5, ferried in by submarine on a high-priority intelligence mission. His orders were specific: examine any American electronic equipment, particularly radar, that the Marines might have left behind when they were inevitably driven off the island. Naval intelligence in Tokyo had received fragmentary reports about advanced American radar systems. Hard evidence was desperately needed. What Yasuda found shocked him to his core. The radar was an SCR-268, a U.S. Army fire control system used to direct anti-aircraft guns and searchlights. It sat there in its emplacement, largely intact despite efforts to destroy it before the American withdrawal. The antenna array, mounted on a rotating cross-shaped platform, was far more sophisticated than anything in Japanese service. The transmitter and receiver units, when Yasuda carefully disassembled them, revealed components and design principles that Japanese engineers were still struggling to achieve. But it was the specifications, recovered from partially burned technical manuals, that truly alarmed him. The SCR-268 operated at 1.5-meter wavelength, about 200 megahertz. It could detect aircraft at ranges exceeding 30 kilometers. More importantly, it could measure bearing and elevation with an accuracy of approximately 1 degree. This was precision. Japan's radar development program had projected wouldn't be achievable for another year, perhaps 2. Yasuda spent 3 days examining the equipment, photographing every component, copying every page of documentation he could find, before the threat of American counterattack forced him to evacuate. He returned to Tokyo with crates of components and rolls of film that would keep Japanese engineers busy for months. The analysis that followed revealed uncomfortable truths. The Americans weren't just marginally ahead in radar technology. They were operating on fundamentally different principles, using components Japan couldn't manufacture, achieving performance Japan couldn't match. Captain Sudo Hajime, one of the Imperial Navy's leading radar experts, wrote in his classified report to the Naval Technical Research Institute in late September 1942, "The captured American equipment demonstrates sophistication in several key areas. Their electron tubes are of higher quality than our best efforts. Their antenna design shows theoretical understanding we lack. Most concerning, the precision of their range and bearing measurements suggests they may have solved the fire control integration problem we consider insoluble with current technology." The fire control integration problem was well understood by both navies. Radar could detect targets at long range, but using radar to actually control gunfire required solving several technical challenges simultaneously. You needed extremely precise measurements of range and bearing. You needed rapid updates as targets maneuvered. You needed ways to feed that data directly into fire control computers. And you needed reliability, because a system that worked in laboratory conditions but failed in combat was worthless. Japanese radar development had focused primarily on search capabilities, finding enemy aircraft before they could attack, detecting surface ships at night or in bad weather. The Type 21 and Type 22 sets entering service on major warships could do these tasks adequately, but using them to control main battery fire against moving targets at extreme range remained theoretical. The Americans, Pseudo reported, appeared to have made fire control radar practical. This assessment reached the highest levels of the Imperial Navy. Admiral Yamamoto Isoroku, commander of the combined fleet, received briefings on the implications. So did Vice Admiral Fukudome Shigure, chief of the Navy General Staff's Operations Section. The response was a curious mixture of concern and denial. On one hand, orders went out to accelerate Japanese radar development. The Naval Technical Research Institute received increased funding. Priority shipments of raw materials went to electronics manufacturers. Engineers were transferred from other projects to focus on radar. The Type 22, Japan's best shipboard search radar, was rushed into wider deployment. But on the other hand, fundamental assumptions about naval warfare remained unchanged. Japanese doctrine still emphasized night combat, where superior optical systems and extensive training would supposedly negate any American radar advantage. Japanese naval architects still designed ships around massive optical rangefinders and sophisticated mechanical fire control computers that assumed visual target acquisition. The entire structure of Japanese naval tactics, the thing that had made the Imperial Navy so formidable in the war's early battles, was built on the assumption that night combat and bad weather favored Japan. The idea that the Americans might have turned darkness and weather into advantages rather than neutralizing factors wasn't fully grasped. Lieutenant Commander Yoshimura Takashi, a fire control officer who survived the war and later wrote extensively about Japanese naval operations, reflected in 1953, "We knew the Americans had good radar. We knew they were working on fire control applications. But we couldn't conceive that they had solved the problem so completely. Our own efforts at radar-guided fire control were producing marginal results at best. We assumed theirs would be similarly limited. This assumption cost us dearly. The problem wasn't Japanese incompetence. Far from it. Japanese engineers and scientists were capable and innovative. Japan had independently invented radar in the mid-1930s. The Imperial Navy had fielded operational radar systems before the US Navy. But Japan faced insurmountable obstacles in translating theoretical knowledge into mass-produced, reliable, combat-effective systems. The first obstacle was industrial. Radar required high-quality electronic components, particularly vacuum tubes. American industry could produce these tubes in vast quantities with consistent quality. Japan couldn't. Every electron tube required precision manufacturing, rare materials, and quality control that Japanese wartime production facilities struggled to maintain. The captured American tubes were examined microscopically. Japanese engineers marveled at their uniformity, their quality, their performance characteristics. Duplicating them proved impossible with available manufacturing capacity. The second obstacle was theoretical. American radar development benefited from close cooperation between military services, industrial laboratories, and academic research institutions. The MIT Radiation Laboratory, established in 1940, brought together the best physicists and engineers in a focused effort to advance radar technology. Nothing comparable existed in Japan. The Army and Navy developed radar independently, often duplicating efforts. Academic researchers had limited access to military projects. Industrial cooperation was hampered by security concerns and inter-service rivalry. The third obstacle was philosophical. Japanese naval doctrine, refined over decades and validated by early war victories, emphasized human factors, superior training, superior night combat skills, superior offensive spirit. Technology was important but secondary to these human qualities. The idea that American technology might become so superior as to negate Japanese tactical and training advantages contradicted fundamental beliefs about what made navies effective. This philosophical resistance to accepting American technological superiority shows up repeatedly in Japanese naval assessments from 1942 through 1944. Intelligence reports would note American radar capabilities. Technical analyses would document American advantages, but operational planning continued as if these advantages were minor details rather than potential war winners. Part of this was deliberate propaganda. Admitting American technological superiority would undermine morale, so official statements emphasized Japanese strengths, downplayed American capabilities, and assured officers and sailors that spirit and training would triumph over enemy technology. But part of it was genuine belief. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Many senior Japanese naval officers had spent careers mastering tactics and skills that assumed technological rough parity. Accepting that technology could trump expertise meant accepting that their life's work might be obsolete. The consequences of this mindset became clear throughout 1943 as American radar-equipped ships consistently defeated Japanese forces in night engagements. The Battle of Cape Esperance in October 1942 showed the pattern. American ships, guided by SG surface search radar, surprised a Japanese force that ruled these same waters for months. The Battle of Tassafaronga in November saw Japanese tactics triumph despite American radar advantage, but only by using concentrated torpedo attacks before the Americans could bring their radar-directed gunfire to bear. The Battle of Kolombangara in July 1943 pitted American radar against Japanese optical fire control in nearly identical conditions to Nishimura's later disaster at Surigao. The Americans, able to track targets in darkness and rain squalls, achieved gun solutions faster and more accurately than their Japanese opponents. After each engagement, Japanese survivors reported the same phenomenon. American shells arriving with uncanny accuracy in conditions where visual fire control was impossible. American ships that seemed to know exactly where Japanese vessels were despite darkness and weather. American fire control that corrected so quickly it was as if they could read Japanese minds about maneuvering intentions. And after each engagement, Japanese naval intelligence tried to quantify what the Americans had achieved. Commander Mitsui Nakao, assigned to analyze American fire control capabilities after the Battle of Kula Gulf in July 1943, wrote, "Enemy ships appear capable of accurate gunfire at ranges exceeding 18,000 meters in total darkness. Their correction rates suggest continuous tracking of maneuvering targets. We estimate they have achieved integration of radar data with fire control calculators. This represents a significant tactical advantage we currently cannot match." Mitsui's report included a crucial section on estimated American radar performance. Based on observed hits, rates of fire, and corrections for maneuvering, he calculated that American fire control radar must be able to measure range to within 100 meters and bearing to within half a degree. These numbers, which seemed optimistic at the time, would prove, if anything, to underestimate American capabilities. The Mark 8 fire control radar entering service on American battleships in 1944 was actually significantly better than Mitsui estimated. Operating at 3 centimeter wavelength, it could measure range to within 50 meters at distances exceeding 30 kilometers. Its bearing accuracy was approximately 1/4 of a degree. It could track maneuvering targets continuously, feeding data to mechanical computers that calculated firing solutions faster than any human crew could manage manually. But Japanese intelligence in 1943 had no way to know precise specifications of systems they had never captured and couldn't examine. All they could do was observe effects and try to reverse engineer probable causes. The conclusions they reached were accurate in broad strokes but understated the magnitude of American superiority. This underestimation had operational consequences. When Japanese commanders planned night engagements, they assumed some American radar advantage, but not the overwhelming superiority that actually existed. They planned to close ranges quickly, to use torpedoes and superior night fighting skills to offset enemy technology. These tactics had worked, barely, in some engagements. They would fail catastrophically at Surigao Strait. The captured SCR-268 from Guadalcanal did eventually lead to Japanese copies. The Ta-Chi-1 and Ta-Chi-2, ground-based fire control radars, entered service in 1944. They were based on American principles, with Japanese components and engineering. They worked, after a fashion. But they arrived 2 years after the Americans had already moved beyond the technology they copied, and they never achieved the reliability or performance of their American inspiration. Meanwhile, American radar development accelerated. The Mark 8 fire control radar was just one development among many. American ships gained better search radars, better aircraft detection, better target tracking, better integration between systems. By mid-1944, American cruisers and battleships could detect, track, and engage multiple targets simultaneously at night or in bad weather, with accuracy that seemed almost supernatural to Japanese observers. The gap was widening, and it was unbridgeable. Japan simply couldn't match American production, American innovation, or American resources. Japanese engineers knew this. Intelligence officers knew this. Some senior commanders privately acknowledged it. But the institutional momentum of the Imperial Navy, the demands of military tradition, and the political impossibility of admitting defeat meant operations continued, as if Japanese determination could somehow overcome American technology. It couldn't. The proof would come in Surigao Strait, where Rear Admiral Nishimura sailed into an engagement he couldn't win because he couldn't comprehend how completely American radar had transformed naval warfare. But before Surigao, there were other indicators, other warnings, other engagements where the pattern showed itself to anyone willing to see. In February 1944, American carrier aircraft struck Truk, Japan's Gibraltar of the Pacific. Japanese radar detected the incoming raids, but too late and with insufficient precision for effective fighter direction. In the Battle of the Philippine Sea in June 1944, American radar-directed fighter control turned the engagement into the Great Marianas Turkey Shoot, destroying hundreds of Japanese aircraft, while American planes operated under precise radar guidance. By October 1944, when Admiral Toyoda Soemu, commander of the Combined Fleet, planned the Shogo operation that would send Nishimura into Surigao Strait, Japanese naval intelligence had documented American radar capabilities extensively. They knew the Americans had superior search radar. They knew American ships could shoot accurately in darkness. They strongly suspected American fire control integration was far more advanced than anything Japan had achieved. But knowing and acting on that knowledge were different things. The Shogo plan still assumed Japanese forces could close to ranges where superior torpedo armament and night fighting skills would tell. It still assumed American technological advantages could be overcome by tactical audacity and aggressive spirit. It still assumed the psychological weight of samurai tradition and Bushido spirit counted for something against radar-guided 16-inch guns. Admiral Nishimura knew about American radar when he sailed into Surigao Strait. He'd read intelligence assessments. He'd received briefings. His flagship carried Japanese radar that was supposed to help counter American advantages. But abstract knowledge couldn't prepare him for the reality of facing an enemy who could see perfectly in absolute darkness, who could calculate firing solutions faster than the target could maneuver, who could hit what they couldn't see. In those final minutes on Yamashiro's bridge, as shell after shell tore through his flagship with impossible accuracy, Nishimura finally understood what the intelligence reports had been trying to tell him for 2 years. The Americans hadn't just improved naval warfare technology, they'd transformed it. They'd made darkness and distance into advantages. They'd turned the night, which had been Japan's ally, into an enemy that killed with mechanical precision. The battleship rolled to port, fires consuming her, water flooding through dozens of shell holes, men scrambling desperately toward any exit from the doomed ship. On the bridge, Admiral Nishimura stood at attention, gripping the railing as the deck tilted beneath him. His staff officers, those still alive, stood with him. There would be no abandoning ship for the Admiral and his immediate subordinates. That wasn't how Imperial Navy officers faced defeat. As seawater rose around his boots, Nishimura looked one last time toward the northern horizon, where American muzzle flashes still lit the sky. His ships had never gotten close enough for visual fire control to work, never gotten within range where Japanese gunnery skills could have mattered. The Americans had killed them from a distance, in darkness, with a precision that made mockery of everything he'd learned about naval warfare in 30 years of service. Then the water closed over the bridge, and Rear Admiral Shoji Nishimura became another casualty of a war that Japan had lost the moment it began, even if that loss took years and hundreds of thousands of lives to become undeniable. But the story of Japanese encounters with American radar technology didn't end at Surigao Strait. The survivors of that one-sided massacre brought back detailed reports. Officers who had watched their ships die under radar-directed fire finally had concrete evidence of exactly how wide the technological gap had become. And in the desperate final months of the war, Japanese engineers and tacticians attempted to devise countermeasures to an American advantage they could no longer deny. These final attempts, launched far too late and with far too few resources, reveal perhaps more clearly than anything else the tragedy of Japan's technological and industrial limitations in World War II. In November 1944, survivors from Surigao Strait were extensively debriefed at the Naval Technical Research Institute in Tokyo. Captain Shinoda Matsuo, who had commanded Yamashiro and miraculously survived her sinking, provided testimony that was classified as most secret and circulated only among the highest military and technical leadership. His account was devastatingly specific. The Americans had opened fire at ranges Shinoda estimated at 22,000 yards, approximately 20 kilometers. They had achieved straddles with their first or second salvos. They had corrected for Yamashiro's evasive maneuvers so quickly that it appeared they were tracking continuously. The accuracy had remained consistent despite darkness, despite rain squalls, despite smoke and chaos. And most telling, the Americans had maintained fire control on multiple targets simultaneously. They weren't just hitting Yamashiro. They were hitting Mogami and the destroyers with similar accuracy, suggesting multiple fire control systems operating independently and effectively. Shinoda's conclusion was unambiguous. The enemy possesses radar fire control systems of such sophistication and reliability that they render night combat suicidal for our forces. Our optical fire control, regardless of crew skill or training, cannot function at the ranges where their radar allows accurate gunnery. Our own radar equipment cannot match their performance. Unless we develop effective countermeasures or achieve technological parity, night surface engagements against American forces should be avoided at all costs. This recommendation, coming from a senior surviving officer of one of the war's most one-sided naval defeats, carried weight. The question was, what could be done about it with Japan's dwindling resources and shrinking defensive perimeter? The answer, in the final analysis, was very little. Japanese efforts to counter American radar fell into three categories. First, develop better Japanese radar to match American capabilities. Second, develop electronic warfare techniques to jam or deceive American radar. Third, develop tactics that would minimize American radar advantages. All three efforts faced nearly insurmountable obstacles. Radar development continued through the end of the war, but always 2 years behind American advances. The Type 22 search radar, Japan's best shipboard system, had been cutting-edge when introduced in 1942. By 1944, it was obsolete compared to American equipment. Efforts to develop fire control radar comparable to the American Mark 8 never progressed beyond prototypes. The industrial capacity to mass-produce such sophisticated systems simply didn't exist in wartime Japan. Moreover, Japanese radar development suffered from a fundamental resource problem. The raw materials for high-performance electronics, particularly rare earth elements and high-grade metals, were increasingly scarce as American submarines strangled Japan's maritime supply lines. The manufacturing facilities capable of producing precision components were priorities for B-29 bombing raids. and the electrical power grid required to run radar equipment was increasingly unreliable as the war ground on. Electronic warfare efforts showed more promise, but faced similar resource constraints. Japanese technicians developed chaff, the aluminum foil strips that created false radar returns. They experimented with radar jammers. They even achieved some tactical successes, particularly against American aircraft radar, in the Solomons Campaign of 1943. But these countermeasures were always reactive, always behind the curve of American technological development, and never produced in quantities sufficient to meaningfully affect American operations. The tactical response was perhaps most revealing of Japan's predicament. If you couldn't match American radar and couldn't effectively jam it, you had to find ways to fight that didn't rely on the night combat advantages that had served Japan so well early in the war. But the Imperial Navy's entire tactical doctrine, its training regimen, its operational planning, was built around night combat. Abandoning that advantage meant abandoning the one area where Japanese forces were still competitive. Some commanders understood this dilemma and adjusted their tactics accordingly. Others continued to plan as if the early war successes could somehow be repeated through superior fighting spirit. The latter approach led to disasters like Surigao Strait. But even the more realistic commanders faced an inescapable problem. American radar advantages weren't limited to fire control. American search radar detected Japanese ships earlier and more reliably. American aircraft detection gave warning that allowed fighter direction and anti-aircraft defense far superior to Japanese capabilities. American radar-equipped aircraft could hunt submarines with devastating effectiveness. The technological imbalance affected every aspect of naval warfare. By early 1945, with American forces approaching the Japanese home islands, the radar gap had become one part of a broader technological chasm. American ships had better damage control, better fire suppression, better compartmentalization. American aircraft had better engines, better radios, better instruments. American submarines had better torpedoes, better sonar, better operational range. American logistics allowed sustained operations at distances that would have exhausted Japanese capabilities even if the ships themselves had been equal. The pattern was consistent across every measurable category. America's industrial might, once fully mobilized, had produced not just more equipment, but better equipment. Japanese engineers and servicemen, despite equal intelligence and equal courage, couldn't bridge a gap created by America's overwhelming advantage in resources, industrial capacity, and scientific collaboration. Understanding this disparity helps explain why Japan's military leadership became increasingly desperate in the war's final year, why kamikaze tactics emerged, why last-ditch defensive operations were planned with no realistic hope of success. They were facing an enemy who could see in the dark, shoot accurately at impossible ranges, and absorb losses that would have been crippling to Japanese forces. The technological balance had tilted so far that conventional tactics no longer offered any path to victory. At the Naval Technical Research Institute in Tokyo, engineers continued working on advanced radar projects even as American bombs fell closer and American invasion seemed inevitable. They knew their efforts were futile, that whatever they developed would arrive too late and in too small quantities to affect the war's outcome. But they worked anyway, driven by professional pride and a desire to at least understand the technology that had defeated them. After Japan's surrender in August 1945, American technical teams fanned out across the home islands examining Japanese military technology. What they found in radar laboratories and research facilities surprised many of them. The Japanese weren't ignorant or backward. They understood the theoretical principles. They had developed innovative solutions to specific problems. What they lacked was the industrial capacity to turn theory into mass-produced, reliable, combat-effective equipment. The captured Japanese radar systems were examined with the same care that Japanese engineers had given captured American equipment 3 years earlier. American analysts noted the clever design choices forced by component shortages. The innovative antenna configurations, the workarounds for lack of high-quality electron tubes. It was the work of capable engineers trying to achieve impossible goals with inadequate resources. One American radar specialist, examining a Japanese Type 22 system in September 1945, wrote in his report, "This equipment demonstrates sophisticated understanding of radar principles. The engineering is competent given the constraints under which the designers obviously worked, but it's generations behind what we were fielding by 1944, not because they couldn't understand the technology, but because they couldn't manufacture the components or integrate the systems at scale. They lost the radar war before it started, not through lack of knowledge, but through lack of industrial capacity." This analysis captures the essential tragedy of Japan's technological position in World War II. The radar gap that killed Admiral Nishimura and thousands of other Japanese sailors wasn't created by inferior scientists or incompetent engineers. It was created by industrial and economic realities that no amount of fighting spirit or tactical ingenuity could overcome. Japan had entered a technological war against an opponent with 10 times the industrial capacity, unlimited resources, and scientific collaboration that produced innovation at a pace Japan couldn't match. The specific case of radar fire control, where American ships could hit targets they couldn't see at ranges where Japanese fire control was useless, exemplified a broader pattern. In tanks, aircraft, submarines, communications equipment, logistics systems, practically every measurable category of military technology, American equipment pulled ahead of Japanese equivalents as the war progressed. The gap visible at Surigao Strait in October 1944 existed across the board. This technological imbalance determined the war's outcome as surely as any strategic decision or tactical brilliance. Japan had seized the initiative early through careful planning and aggressive execution, but once America's industrial and technological superiority came fully into play, Japan's defeat became mathematical inevitability. The radar-equipped American battleships at Surigao Strait were just one symbol of that larger reality. For the men who sailed into Surigao Strait that dark October morning, technological explanations offered no comfort. They died because American radar could see them while they sailed blind. They died because American fire control could hit them while they fired wild. They died because the institutional momentum of the Imperial Navy drove them into an engagement where courage and skill couldn't overcome the enemy's ability to shoot accurately in absolute darkness. The 10 survivors pulled from the oily waters at dawn carried that knowledge with Percet 5. The Americans who rescued them treated their wounds and gave them water and asked respectful questions about the battle. Some of those questions concerned radar. What type of sets did Japanese ships carry? What ranges could they detect targets? Did Japanese radar affect fire control? The survivors answered honestly. Their war was over. There was no military advantage in concealing information about systems the Americans would soon examine in detail anyway. They described the Type 22, its limitations, the desperate hope that somehow Japanese optical excellence would compensate for American radar superiority. The shock of discovering that hope was futile. Those interrogations, classified and filed away until decades after the war, provide a human perspective on the radar gap, not technical specifications or strategic analysis, but the voices of men who had experienced firsthand the terror of facing an enemy who possessed what seemed like supernatural abilities to see and shoot in darkness. One survivor, a gunnery officer, whose name was redacted from the declassified reports, said, "We trained for night combat our entire careers. We believed we were the best in the world at it. Then the Americans showed us that all our training meant nothing against their technology. They saw us perfectly. We were blind. They hit us with their first salvos. We never even acquired a proper target. It wasn't combat. It was execution." That testimony, raw and bitter, captures the psychological impact of the technological imbalance as clearly as any after-action report or intelligence analysis. Japanese officers had built their professional identities around night combat expertise. Discovering that American technology had made that expertise obsolete wasn't just militarily devastating, it was personally crushing, a fundamental challenge to their sense of professional competence and self-worth. The few senior Japanese naval officers who survived the war carried similar burdens. They had led men into battles they couldn't win, using tactics that American technology had rendered obsolete. Some dealt with that knowledge through post-war careers focused on understanding what had gone wrong. Others retreated into silence, unable to reconcile their memories of combat with the reality of technological inadequacy. Captain Sudo Hajime, the radar expert who had analyzed the captured SCR-268 back in 1942, survived the war and continued his technical career into the 1950s. In a 1956 paper published in a Japanese engineering journal, he reflected on the radar gap with clinical detachment that couldn't quite mask deeper regrets. The disparity between American and Japanese radar capability in World War II represented not merely a technological gap, but a systemic failure of Japanese industrial and scientific organization. We understood the principles. We could not implement them at scale. This pattern, visible in radar development, characterized our entire war effort. Superior American industrial organization, scientific collaboration, and resource availability created advantages we could observe, but not counter. The consequences were predictable and catastrophic. Sudo's analysis was technically correct, but it couldn't capture the human cost of that systemic failure. The thousands who died at Surigao Strait and dozens of other engagements where American radar superiority proved decisive. The pilots shot down by radar-directed anti-aircraft fire, the submariners killed by radar-equipped patrol aircraft, the soldiers killed by naval gunfire directed with a precision impossible without radar. All of them casualties of an industrial and technological imbalance that transcended individual courage or competence. For Japan, the radar gap symbolized a larger truth about the war. They had entered conflict with an enemy they couldn't match industrially or technologically. Early tactical brilliance had created an empire, but sustaining that empire against an opponent with America's resources had always been impossible. The radar that allowed American ships to shoot accurately in darkness was just one manifestation of systemic superiority that doomed Japan from the war's beginning. Admiral Nishimura probably understood this in his final moments, standing on Yamashiro's sinking bridge as water rose around him. The shells that had torn through his flagship with impossible accuracy in absolute darkness weren't just technologically superior weapons. They were proof that Japan had already lost a war that would continue for 10 more months and hundreds of thousands more casualties before the inevitable end arrived. The tragedy of Surigao Strait wasn't that Japan fought bravely. They did. It wasn't that they lacked skill or tactical competence. They had both. The tragedy was that courage and skill couldn't overcome American technology, that Japan's finest warships and most experienced crews sailed into darkness that had become their enemy, armed with weapons and tactics that had been rendered obsolete by an opponent they couldn't see and couldn't match. Those 10 minutes of radar-directed slaughter in Surigao Strait, where American battleships destroyed a Japanese force without ever seeing them visually, represent in microcosm the entire Pacific War's fundamental reality. Japan couldn't win a technological war against America. The radar-guided shells that killed Admiral Nishimura were just delivering a verdict that had been inevitable since Pearl Harbor, regardless of how long the actual fighting lasted. In modern naval museums, carefully preserved examples of World War II-era radar equipment sit as monuments to technological revolution. American Mark 8 fire control radars, their antennas and transmitters frozen in museum pieces, look crude by contemporary standards. But in 1944, they were miracle machines that could see through darkness and weather, that could guide shells onto targets 20 miles away with precision that seemed impossible. Japanese Type 22 radars sit in other museums, usually with explanatory placards noting their innovative features and the constraints under which they were developed. They're presented as evidence of Japanese technical competence, which is accurate, but the unspoken context is that these competent systems were hopelessly outclassed by American equipment, that the engineers who designed them were trying to catch up with opponents who had already moved beyond what they were attempting. The radar gap was just one aspect of Japan's technological disadvantage, but it was among the most visible and most psychologically devastating, because radar transformed the one area where Japan had maintained superiority into yet another American advantage. Night combat, Japan's specialty, became suicide against radar-equipped American forces. The darkness that had concealed and protected became transparent and deadly. The shells that fell on Yamashiro that October morning were guided by invisible beams that saw what human eyes couldn't. They arrived with mechanical precision that human skill couldn't match. They transformed night combat from a test of training and courage into a technological slaughter, and they killed Admiral Nishimura and 2,000 other Japanese sailors, with an efficiency that marked the end of one era of naval warfare and the beginning of another. That transformation, born in American industrial laboratories and perfected in combat against an outmatched opponent, changed naval warfare forever. But for the men who died in Surigao Strait's dark waters, unaware of the historical significance of how they died, the technology meant simply that courage and skill no longer mattered. The enemy could see them, they couldn't see the enemy. The rest was inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.